In this video, we're continuing our discussion of ordinary differential equations. And here we're discussing solution methods for boundary value problems. In particular, we are going to discuss the shooting method. So the shooting method was introduced in the previous lecture video considering methods for solving boundary value problems. And here we are going to discuss this method in a bit more detail. So let's consider a second order ODE with the boundary conditions defined as follows. So y double prime is a function of x, y, and y prime, with boundary conditions defined at the ends of the domain. Y of 0 is equal to y0, and y of L is equal to yL. So let's reduce this to two first-order equations. Let's define u is equal to y, and v is equal to y prime. So u prime is equal to v, and v prime is equal to our function of x, u, and v. And our boundary conditions become u of 0 is y0, and u of L is yL. To solve this system with familiar methods for initial value problems, we must replace the condition u of L is equal to yL with the condition for v of 0. Because if you recall, to use the methods for solving initial value problems, all of our initial conditions must be defined at the same point, which is 0 of the independent variable. So we use a guess for v of 0 and solve both equations until x is equal to L. At this point, u of L is compared with our prescribed boundary condition yL. If the agreement is not satisfactory, and it is likely that it is not going to be unless your guess is very good, another guess is made for v of 0, and an iterative process is repeated. For linear problems, this iterative process is very systematic and only 2 iterations are needed. So for example, consider the general second order linear equation. So y double prime is a function of x plus a of x, y prime of x, plus b of x, y of x is equal to f of x. So this is a linear second order differential equation. And our prescribed boundary conditions y of 0 is equal to y0 and y of L is equal to yL. So let's denote two solutions of the equations as y1 of x and y2 of x. And these can be obtained using our initial guesses. So the initial guess for y at 0 is equal to y0 in both cases. So y1 of 0 equals y2 of 0 is equal to y of 0, which is y0. And two different initial guesses for y prime of 0. Since the differential equation is linear, the solution can be formed as a linear combinations of our two solutions, y1 of x and y2 of x. So y of x is equal to c1 y1 of x plus c2 y2 of x, where c1 plus c2 is equal to 1. So now we require that y of L is equal to yL. So this in turn requires that c1 y1 of L plus c2 y2 of L is equal to yL. So what we're requiring here is that our solution to our equation, when evaluated at x is equal to L, is equal to our prescribed boundary condition, yL. So we can note that y1 of L and y2 of L have known numerical values from the solutions y1 of x and y2 of x, which have already been computed. So this means that we have two linear equations for c1 and c2. So the solution to these is given as shown here. So c1 is equal to yL minus y2 of L over y1 of L minus y2 of L, and c2 is defined similarly. So we can plug these expressions for our c1 and c2 into our general solution for y of x, and this gives the desired solution to the ODE. So this shows how with only two guesses, or two iterations of our guesses, we can reach the final solution for our ODE if the original ODE was linear. Now for nonlinear ODEs, several iterations are needed to obtain the solution at L to within a prescribed accuracy. And we can use a secant method to guide our iterations. So to illustrate this, consider the value at x is equal to L, which we can call y of L, as a nonlinear function of y prime of 0. So if y prime of 0 is our input, we can choose different values of y prime of 0 and get some values of y of L. So then with a bunch of different values, we can plot this function. So this function can be described numerically by choosing several initial guesses for y prime, which is y prime of 0, and obtaining the corresponding y of L's. So we can just see this graphically and numerically here as this function. So if we choose two initial guesses, or if we have two guesses, y1 prime of 0 and y2 prime of 0, then we can find y3 prime of 0 from the line that passes between these 2 points. So the equation of this line is given as shown here, where m here is the reciprocal of the slope. So this is the slope of this line. And that's the equation of the line passing between those 2 points. And now we want to see where this line intersects our point, or this value y of L. And that will help us to find our y3 prime of 0, which will be our next guess. So y3 prime of 0 is going to be y prime 2 of 0 plus m yl minus y2 of L. And then we can continue to iterate with successive guesses following from the equation shown here. So in this case, if we're looking for y prime of alpha plus 1, y prime of 0 of alpha plus 1, based on our previous two estimates, alpha and alpha minus 1. So where this m alpha minus 1 is given as shown here. And this process continues until y alpha of L is sufficiently close to y of L. And it can be noted that convergence can be a bit of a problem if y of L is a very steep function of y prime of 0. So let's look at an example. A laminar boundary layer on a flat plate is called the Blasius boundary layer, is given by the solution, which is f of eta, f is a function of eta, to this differential equation. So the third derivative of f plus f times the second derivative of f is equal to 0, where again f is a function of eta. The boundary conditions are derived from the physical boundary conditions on the fluid. So the no-slip condition at the wall says that f prime of 0 is equal to f of 0 is equal to 0. And free stream conditions at large distances from the wall says that f prime at infinity is equal to 1, where here eta equals 0 at the wall, and eta is large far from the wall. So to solve this by the shooting method, we can first define our three functions. So f1 is equal to f double prime, f2 is equal to f prime, and f3 is equal to f. So we can rewrite our differential equation, our single third order differential equation, as three first order ODEs. So f1 prime is equal to minus f1 f3, f2 prime is equal to f1, and f3 prime is equal to f2. And we can write our initial conditions for these three functions. So f2 of 0 is equal to 0, f3 of 0 is equal to 0, and we don't know what f1 of 0 is equal to, because f1 of 0 was prescribed initially as this boundary condition at infinity. But we want this to express this as an initial condition. So we need to figure out we need to guess something and figure out what should f1 of 0 be. So we guess in f1 of 0 and see what we get for f2, which is f prime at large eta. So we can repeat until f2 equals 1 at large eta. Because that gives us our f2 is this condition here. So we don't have a condition for f1 at 0, so we're going to guess a condition for f1 at 0, and then look at f2 at large eta and make sure that it equals our prescribed boundary condition. Now, if we look at F2 versus eta, when we solve this problem, we can see that for this problem, eta equals 10 is large enough. So that's we can evaluate our F2 at eta equals 10. So let's choose two initial guesses. F1 of 0 is equal to 1, and F1 of 0 is equal to 0.5. And then we can calculate F2 as a function of eta using our traditional methods for initial value problems. So for example, we can use the fourth order Runge-Kutta method with a step size delta eta is equal to 0.01. And then we can iterate to get our next guess using the CCAT method as shown here. So you can see that when eta is large, we're using 10 for these values. And we can define some convergence criteria that looks at, basically compares our F2 at large eta, if F2 at 10, with what we said F2 needs to be at large eta, which is 1. So if this difference, or this error, is less than or equal to some prescribed error tolerance, then we can stop our iterations. So if we proceed like this, the solution that we get says that F1 of 0 is equal to 0.469600, which agrees with the accepted solution. And if we plot the, this shows a plot of f prime, and f double prime for as a function of eta, which is known as the Blasius profile.